Once again, hello from Bucharest. I'm very happy and honored to chair this session. And let's start with a talk given by Professor Osamu Sato from Kyushu University in Japan. Professor Sato is very well known in our community because of his achievements in material science, crystal engineering, design of molecular materials based on azobenzene derivatives, as well as on magnetic materials, especially switchable molecule-based magnets. Professor Sato, you have the screen.
Okay, thank you, Professor Andrew, and thank you for giving me opportunity to talk my recent works. Can you hear me? Okay. And can you see PPT? Okay, okay. Okay, I'm Osamu Sato from Kyushu University. I talk about magnetization and polarization switching, especially polarization switching material. And as you know, various functional molecular compounds have been developed, including magnetic compounds and polarization switching material. And we aim to synthesize new compounds whose physical properties can be controlled by external stimuli, such as temperature and light irradiation, especially magnetic compound and polarization compound. And as switching mechanism, we use spin transition, electron transfer, proton transfer, and molecule reorientation. And previously, and coupling of them, such as electron transfer coupled spin transition and proton transfer coupled spin transition. And previously, we reported several magnetic compounds and switchable magnetic compounds. And one example is shown here. We reported electron transfer iron cobalt complex. This complex exhibits electron transfer by temperature change and photoirradiation. And after photoirradiation, this complex exhibits a single chain magnet behavior. And we also reported high-spin molecules where iron 3 high-spin state interact ferromagnetically and forming a high-spin state S equal 90/2. This is one of the largest high-spin molecules reported thus far. And furthermore, we reported this new high-spin nanocage compound. And importantly, this iron site is partially reduced. So this is mixed valence state. So this molecule exhibits rapid intramolecular electron hopping. This is confirmed by Metzbauer spectroscopy, as shown here. These two signals merge into unique doublet. So this means electron hop around this atomic layer shell, and the hopping rate is faster than Metzbauer time scale, 10⁻⁸. And we reported several other magnetic compounds. And more recently, besides magnetization switching material, we are developing polarization switching material using electron transfer. So today I'm going to talk about 3 compounds: cobalt chromium dinuclear complex, cobalt complex, iron cobalt complex. They exhibit polarization switching. And the first topic is this polarization switching observed in this cobalt chromium complex. And as you know, polarization switching is observed in ferroelectric compound, and major mechanism is ion displacement. And its polarization can be controlled by electric field. And in this study, we aim to synthesize new polarization switching material using electron transfer. As shown here, electron transfer is the source of polarization instead of ion displacement. And the advantage is electron transfer can be directly controlled by photoirradiation. And we also use non-ferroelectric compounds, Valence Tautomeric compounds, because of its better designability. And now we talk about polarization switching material using electron transfer. And to realize electron transfer, polarization switching using electron transfer, we focus on this cobalt Valence Tautomeric compounds. This compound exhibit electron transfer between metal and ligand. Cobalt 3 and cobalt 3, 2. So these molecules exhibit dipole moment switching at a molecular level. And furthermore, this dipole moment switching is induced by photoirradiation. However, at a macroscopic level, this polarization cancels out. Therefore, to realize macroscopic scale polarization switching, we should control electron transfer direction. We should realize directional electron transfer. So to realize polarization switching using electron transfer, we designed heterometallic cobalt chromium dinuclear complex using chiral ligand. Cobalt complex with RR chirality and chromium complex SS CTH ligand and synthesized heterometallic cobalt chromium complex. And cobalt complex has already been reported, and we analyze single crystal structure. Then these are SS ligand and RR ligand, and this is SS ligand and RR ligand, SSRR, align alternatively as shown here, and the cobalt is here. And now we exchange this cobalt side with chromium. This is exchange from cobalt to chromium. So this means this cobalt side is changed to chromium and chromium. This means molecules oriented in the same direction in the crystal. So if these molecules exhibit electron transfer, then it is directional, always from center to left. So we investigate this charge transfer property and polarization switching property. And this is magnetic property. And as shown here, this complex exhibit electron transfer, Valence tautomerism from ligand to metal. Low temperature, cobalt 3, chromium 3. Heating, cobalt 2, chromium C because of electron transfer. And dipole moment is nearly 0. But this is dipole moment 9. So these molecules exhibit dipole moment switching between 0 and 9. This is molecular level switching. And as I mentioned, these molecules oriented in the same direction. Cobalt, chromium, cobalt, chromium, cobalt. So this electron transfer should be directional, as shown here. So this transition is directional and non-polar structure transformed to polar structure. So this means polarization switching via electron transfer is induced. And this is a new polarization switching material using electron transfer. And the advantage of electron transfer over ion displacement is that electron transfer can be directly controlled by photoirradiation, as shown here. So this means ultra-fast polarization switching is expected. So we measured a photo-induced effect using IR pump probe spectroscopy at room temperature. And this is a difference IR spectra before and after photoirradiation. And this is a difference IR spectra between high temperature phase and low temperature phase. And this spectra is consistent with this one. This means electron transfer is induced by photoirradiation. And this electron transfer is completed less than 2 picoseconds. So this means polarization switching occurs less than 2 picoseconds. And to characterize the faster process, we measure the photo effect using femtosecond time-resolved absorption spectroscopy. And as shown here, after irradiation, absorption change, and it decay with a time scale of 280 femtoseconds. So this means polarization switching is induced this time scale. So this molecule is irradiated, then photo-induced directional electron transfer is induced from here to Cobalt-3 site and forming polar state. And the time scale is 280 femtoseconds. So ultra-fast photo-induced polarization switching is induced in this cobalt chromium single crystal. And as I mentioned, ferroelectric compound polarization is observed, switching is observed, but now we realized polarization switching using electron transfer, using directional electron transfer, and furthermore, polarization switching is induced by photoirradiation. Okay, this is the first topic. And next, I'm going to talk about polarization switching of cobalt complex and its pyroelectric property. And ferroelectric compounds have many interesting properties. One of them, pyroelectricity. Polarization change is detected by current. And in this study, we investigate the pyroelectric property, electron transfer-based pyroelectric current, this non-ferroelectric polarization switching material, this cobalt mononuclear complex. And we synthesize this complex, and this is single crystal structure. And this is polar space group and molecules oriented in the same direction as shown here. And these molecules exhibit Valence tautomeric behavior. At high temperature, cobalt-2 high spin state, on cooling, electron transfer is induced, forming cobalt-3 state. So this is a Valence tautomeric behavior. Transition is about around 300 Kelvin. And as I mentioned, this molecule has a polar structure. This crystal has polar structure. So this electron transfer is directional. Electron transfer occurs from ligand to metal, as shown here. So this compound exhibits polarization switching. The origin is electron transfer. And we try to measure pyroelectricity. Low temperature phase cobalt-3, so large polarization. On heating, electron transfer is induced and cobalt-2 state, and its polarization is smaller than this one. Therefore, this change is detected by as current. So we investigate the pyroelectric property using this single crystal. And this is the result. Pyroelectric coefficient is blue, and this red is derivative of chi-T value. This blue and red is almost consistent. This means pyroelectric current originating from electron transfer, Valence tautomerism, is detected. And this is a change in polarization, blue, and change in chi-T value, red. And the DFT calculation shows that low temperature phase 13 debye dipole moment, high temperature 7. And this difference is detected as pyroelectric current, as shown here. intermolecular electron transfer converts to pyroelectric current. And furthermore, this compound exhibits light-induced polarization switching, and this process is very fast from IR pump probe spectroscopy. So we reported pyroelectric current of this Valence Tautomeric compound with polar structure. And usually it is difficult to control transition temperature of ferroelectric compound, but this is Valence Tautomeric compound. So if we control ligand redox potential, then we can control transition temperature. This means pyroelectric current temperature is controllable. This is advantage over typical ferroelectric compound. Okay, next I'm going to talk about polarization switching using spin transition. Now I talk about polarization switching using electron transfer. But as you know, there are many more dynamic electronic processes, and they can be used as a source of polarization switching. And in this study, we investigate the polarization switching using spin transition in polar molecular structure. And spin transition is accompanied with electron redistribution within the orbital and also metal and ligand. So spin transition in polar molecular structure should exhibit dipole moment change, which should be detected as polarization switching. So we investigate the polarization switching behavior of spin transition compound. And we designed this molecule, iron N4O2. This is because N4O2, this molecule exhibits spin transition. So we designed this iron 3 spin crossover complex. And we synthesize heterometallic dinuclear complex, iron and cobalt. And as in iron cobalt chromium complex, this molecules has polar structure and molecules oriented in the same direction. Iron, cobalt, iron, cobalt, iron, cobalt. And this complex exhibit spin transition behavior. This is iron 3, but this complex has strong covalency between metal and ligand. And this complex exhibits spin transition at around 90 Kelvin, low spin and high spin state. And this spin transition is confirmed by a metal ligand bond length change from single crystal analysis. And furthermore, this change is detected by X-ray absorption spectroscopy, iron side change as shown here. And we measured pyroelectric property of this spin transition behavior using this single crystal. And then this is the result. And as you can see, large pyroelectric current is clearly detected at spin transition temperature, 90 Kelvin. So this means this compound exhibits polarization switching. The origin is spin transition, as shown here. And as I mentioned, spin transition is accompanied with electron redistribution, not only d orbital, but also ion ligand bond. So this change induces polarization change of this molecule, dipole moment switching. And furthermore, this compound has strong covalency, d-pi hybridized orbital. This strong covalency greatly contributes the large change in dipole moment of this spin crossover complex. And furthermore, we observed interesting polarization switching behavior above spin transition temperature. As shown, as I mentioned, this complex exhibits spin transition here, and above spin transition, below spin transition, almost no change. However, when carefully looking at this pyroelectric property, we detected nearly constant current. And this is an expanded structure. So this is hidden process by magnetometry, but it is detected by pyroelectric current. And this process should be accompanied with a polarization change. So we characterize this process using IR spectroscopy above 100 Kelvin, above spin transition temperature, then THBQ3 minus. This peak decrease with increasing temperature, and this peak increase with increasing temperature. This suggests electron transfer is induced above 100 Kelvin. Gradual charge transfer occurs. And this is confirmed by mass-power spectroscopy. Quadrupole splitting increase with increasing temperature. This means excited iron 2 high-spin state is populated with increasing temperature. This is the origin of the pyroelectric current. And this is interesting compound. Spin transition occurs at around this temperature, and then electron transfer is induced. And this is detected by current, as shown here. So in summary, many magnetization switching material have been reported, and now we reported polarization switching material using electron transfer. And it shows polarization switching and magnetization switching. And we observed ultra-fast polarization switching, pyroelectric current, and nearly constant pyroelectric current. And this is our co-workers, and I would like to thank all of these co-workers, and this is our group member. Thank you for your attention.
Thank you very much, Professor Sato, for the very exciting presentation. And now the talk is open for discussion, questions. Valentin Novikov.
Thank you. Amazing results. So you've shown beautifully that you can detect polarization switching by pyroelectric current, but you also shown that you can induce polarization switching by radiation. So is it possible to detect photoelectric current somehow?
Photoelectric current? Yes. We are now trying to detect photoelectric current of this system.
Okay, thank you. Great.
Okay.
Next question, Matvey.
Thank you very much. Very interesting indeed. Brilliant talk. Could you please clarify, do I understand correctly that in fact your magnetization is tilted? It's not switched to the opposite direction, or I missed something? So when electron transfer occurs, for example, from cobalt to chromium, so the direction of magnetization becomes tilted in molecular axis. Is that right?
The magnetization tilted? Change direction, me?
Yeah. Well, it's not changed to the opposite, but it changed relative to molecular axis. Is that true, or I missed something?
This is para-electric compound. So, and the chromium and the radical has anti-ferromagnetic interaction. But this is not a three-dimensional ordering.
Mm. Okay, thank you.
Sorry.
Mm-hmm.
So if there are no more questions, please join me to thank Professor Sato for the very nice and interesting presentation. And let's switch to the next speaker, who is a very young and talented scientist from the Indian Institute of Science, Abhishake Mondal.
He's interested in molecular magnetism and especially on systems in showing electron transfer and looking for slow relaxation of the magnetization in the new systems he designed with his group. So Abhishake Mondal will present the lecture with the title Photo and Thermo-Induced Metal-to-Metal Electron Transfer and Slow Relaxation of the Magnetization in Cyanido Bridged Iron Cobalt Systems. Abhishake?
Yeah, good morning, Professor Maria Sandhu. Good morning, all. Can you hear me?
Yes.
Can you hear me? Yeah. So
yes.
My screen is, can you see my screen?
Yes.
Okay. Okay. So let's start. Okay. Good morning, all. First, I would like to thank Sergey and Medve for giving me this opportunity to present our work and also for arranging this nice conference. And I also like to thank my friend and collaborator, Mikhail Kiskin, who has motivated us to present our work in this conference. So I'm going to present my work that is entitled as Metal-to-Metal Electron Transfer and Slow Relaxation of Magnetization in Cyanido Bridge Iron Cobalt System. Before going to the main topic, I'll give you a brief introduction about our group, what we are doing here in IISc Bangalore. So we are working on the magnetic material and switches lab. So we have quite a nice facilities, like we have photomagnetic setup, and we have PPMS, squid magnetometer, and a lot and different types of XRD instrument, also like thin film and low temperature powder XRD, high temperature also, and single crystal XRD as well. And there are many other instruments available in our institute. So we are working also, some of our group members, they are also working on the metal-to-metal electron transfer systems, where you can see the
Abhishake, excuse
yes?
me, we still see your first slide. Is it what you would like to show us? Or?
No, this is the second slide. I am in the second slide. Can you see? Can you see my second slide?
Not yet. Can you switch your presentation in a full screen mode?
Just a minute here. Sarah, can you see my presentation? Hello? Can you see my presentation now?
Something is happening.
Can you see my presentation now?
Now it's okay, but you have to switch to slideshow and full screen, yeah?
Now can you see it?
I see only one slide. That's all.
Now can you see it? Hello?
Maybe try to first to make a full screen show and then start your presentation. This helps sometimes.
Now can you see it?
Well, what we see is your second slide and the small features of all your slides at the left. So it's not in the full screen, but we can live with that. Important is try to switch between slides. If it works, let's do it like this.
Can I see it now?
It's still second slide.
Now it's a third slide.
Could you please click on slideshow?
I am in the slideshow mode actually.
So you probably shared not your slideshow, but just general PowerPoint presentation. So you can try to share the screen again, but choose not PowerPoint, but slideshow, which is already run, it seems.
Can you see it now?
We see the second slide. But we didn't start the slideshow.
I think you have to finish your presentation, then see that your slideshow is closed. You have only a general PowerPoint layout. Then you activate your sharing the screen, and then you go to the full screen mode. So when you show your presentation, when you share your presentation in Zoom, it seems that you choose the wrong option.
Now it's okay?
Yes.
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 Sorry for this technical glitch. Yeah, so I'll move this one. So now it's fine, no? Hello?
Now it's okay.
Okay, thank you. So this is a brief introduction of my talk. I'll give you a brief introduction about the systems, and I'll show you the synthesis of iron cobalt systems and the physical properties based on single crystal excited, powder excited, and optical reflectivity, and then magnetic and photomagnetic characterization. And then I'll conclude my talk. So as I mentioned to you that we are working on the molecular vegetable system. So our system can go from one state to another state by the application of external stimuli, and you can switch the magnetic, optical, and the electrical property of the systems. So that Professor Sato already mentioned. So we are also working with single molecule magnets, spin crossover systems, electron transfer systems, and photomagnetic complexes. So today I'll only show you about the mainly electron transfer systems and the little bit about the single molecule magnets. So here is the first evidence of a single chain magnetic behavior of manganese 3 and nickel 2 chain. So here you can see this is a manganese 2 unit. Manganese 3 is connected by this oxygen bridge in the with this ligands, and they are linked with the nickel pyridine aldoxone ligands, and they are having a 1D Ising type of chains, and these molecules or these systems exhibiting first single cell magnetic behavior. Rodolfo and Professor Masaru Yamashita and Hitoshi Miyashita and Professor Claude, they published this one in 2002, and then in 2017 we also studied some with results, some of the physical aspects using neutron diffraction of this interesting single chain magnetic system. And then in 2003, Rodriguez and Professor Michel Fardaghi and Miguel Pulver, they published the first cyanide bridge iron cobalt single chain magnet. Here you can see this is they have used iron BPCN2. This is the cyanide building block, and that is connected with the cobalt 2 systems, with where the cobalt is four side is surrounded by the cyanide nitrogen, and 2 are occupied by the water molecule, oxygen from the water molecules. And here is the microscope image of the single crystals, and you can see the hysteresis with is changing when you change the sweep rate. So this is the first example of iron cobalt single chain magnets. So our strategy, we want to use the single molecule magnet, and we want to connect them with the photomagnetic building block. And you can see the photomagnetic building block, they can have diamagnetic spin state before irradiation, and when you irradiate the light, you can generate a spin on the system. So the system will, you can get the paramagnetic behavior, and you can choose the spin state depending upon the systems as well. So here you can connect to two different single molecule units by a linker. So these linkers, before irradiation or certain temperature, below certain temperature, it will become a diamagnetic. There will be no spin, and you can selectively generate the spin, and this will act as a different type of single molecule magnets. And then you can extend this network by using different linkers. We will get a single shell magnet under irradiation, and also you can, if you link with the you can link them in the 2-dimensional and 3-dimensional, and you can get a 2D or 3D photomagnetic systems where you can have the high DC of the system. And so our idea in this talk, I'll give you, I'll show you something about the single chain magnets, where you can, if you irradiate the systems with light, you will get the, before the irradiation system is almost diamagnetic, but when you irradiate the system with light, particular light, then you can get as a single chain magnet. So, and also another important thing, what you have to check, you have to adjust the redox potential between the metal centers, because metal to metal electron transfer, they are governed with the redox property change of the donor and acceptor. If the donor and acceptor ligand potential is very high, you will never observe the reversible electron transfer. If it's too low, immediately the electron transfer will take place, but it will not go to the reverse effect. So you need to adjust the redox potential between the donor and acceptor. So what we have observed, that if we can modify this donor and ligands, donor and acceptor redox potential roughly around 1 volt, then you can get the reversible electron transfer. So we have choose this cobalt 3 low spin system, that is S equal to 0, and iron 2, this is 3-spherical borate cyanide building block that is synthesized by my supervisor Rodriguez and in 2002. But another interesting thing is that you can go to cobalt 2 high spin state, where you can have S equal to 3 half systems, and that iron 2 also can becoming iron 3, and then you can generate spin here S equal to half system. And when the system is diamagnetic, you can, if you increase the temperature, you will go to the paramagnetic state. Also, you can irradiate the system at low temperature, and you can also get from diamagnetic to paramagnetic under irradiation at one particular temperature as well. So why we choose this iron TP-CN3 building block? This is very interesting property. You can tune, you can see just changing the solvent polarity. You can tune the EHAB value of the system. So here, this is the EHAB value is roughly around 0.8 minus 0.8 volt reduction potential in acetonitrile solvent. And you can see in methanol, the EHAB value is changing almost 0.25 volt. And here also we choose this cobalt ethylene imidazole, ethyl imidazole ligands, and you can see that the EHAB value is roughly around 0.15 volts. So if you see the difference, that is roughly around 0.96 volt, which is almost close to 1 volt. Then what we did, we take these two building blocks and we react them together. We got very nice red color crystals when you use one particular technique. And also when you change the stoichiometry and solvent, we also got green color crystals. But when you saw in the microscope, we observed that there are two different types of crystal. One is block, another one is a plate-like crystal. We separate them mechanically, and we have studied the structure and physical property of the system. And another interesting thing happened. Instead of using vinyl imidazole, when you use ethyl imidazole, we got only one type of crystal, that is needle type of crystal. And you can see the redox potential difference is not that much. It's almost close to 1 volt. Then we have, apart from the single crystal XRD, so for the red crystal, we got this trinuclear unit, where you can see this cobalt 2 is binded with the two different iron metals, iron building block, and you have acetonitrile and water as the crystallization solvent molecules. And in case of the plate green crystals, we got a very interesting zigzag type of chain, where iron TP-CN3 is connected with two cobalt 2 units, where the cobalt is surrounded by 4 imidazole, vinyl imidazole systems. And here is the asymmetric unit. Here you can see we have one BF4 found anion, we have one water molecule that is also connected with the strong hydrogen bonding on the cyanide side, and also we have one acetonitrile molecule in the systems. And when you got the structure of the block, you can see this is almost a wave type of structure. This is not zigzag, and you can see the cyanide linker that is bent, that is not linear. And also here you can see that acetonitrile molecule is not there, but we have BF4 and water molecule, and water is not strongly hydrogen bonding with the cyanide, free cyanide from the iron deficiency. And then another interesting thing happens when you get the structure of the needle. We got a very nice mononuclear motif where you can see the iron deficiency that is in yellow in color, and the cobalt 2 that is connected with the ethyl imidazole that is pink color. And you can see in the middle the cobalt is tetrahedral, and this cobalt is always given in the cobalt 2 high spin state. I'll show you later the magnetic property. And then when you perform the UV spectroscopy in different solvent, then the here you can see at around 420 nanometer you have observed ligand to metal charge transfer transition, but at around 600 nanometer you will observe metal to metal electron transfer between the iron 2 to cobalt 3 center. And you can see this metal to metal charge transfer transition you can tune by tuning just the polarity of the solvent. And when you measure the solid state UVs, you can see the metal-metal charge transfer. We observe approximately the same region, that is 625, and the LMCT is 437. So that means the system is stable in both solution as well as in the solid state. And then when we measure the red crystal, you can see the metal-metal electron transfer is shifted almost 100 nanometers. So that is also very useful information we can get from the UV spectrometer. And then when you measure the magnetic property of this trinuclear unit, you can see that is the system is almost a paramagnetic, and there is no electron transfer is taking place when you cool down the system from 300 Kelvin to the low temperature up to 1.9 Kelvin. And you can see the Kite values matches well to approximately 3.6. That is a combination of iron 3 low spin and cobalt 2 high spin and iron 3 low spin systems. And you can also you can see the at low temperature is also matching with the iron 3 low spin, that is S equal to half system, and cobalt 2 is equal to 3 half, and iron 3 is also S equal to 3 half. They are connected with the antiferromagnetic fashion. And then we studied the optical reflectivity of the the wave chain, that is the green block type of crystals. And you can see that when you decrease the temperature from room temperature to lowest possible temperature in the reflectivity, that is 10 Kelvin, you can see there is almost no change in the reflectivity curve. And we have also irradiated the systems at low temperature, that is 10 Kelvin, using the white light, and you can see the 10 Kelvin curve before and after irradiation, they are superimposable to each other. So that means these systems does not show any photo-induced electron transfer effect even at lowest possible temperature. Then we have performed the magnetic property of this system, and you can see this complex is completely diamagnetic up to 350 Kelvin. And you can see from the M versus H plot at low temperature also, this system is showing perfectly diamagnetic in nature. And then we study the zigzag chain. So there is nothing interesting. You can see this system is also diamagnetic up to 350 Kelvin, and also M versus H plot is showing that the ground state is perfectly diamagnetic. But what is happening when we perform the optical reflectivity measurements at different temperatures? So you can see the blue curve is 280 Kelvin, and the red curve is 10 Kelvin after irradiation, and the black curve is 10 Kelvin before irradiation. You can see there is a huge change, particularly this region, 500 nanometer region, and also 750 region, 50 nanometer region. You can see there is a huge change between the before and after irradiation of the light irradiation of the systems. And you can see we irradiate the systems at 10 Kelvin using the white light, and we plot the absolute reflectivity at 780 nanometer. You can see that almost after 5 hours of light irradiation, the system is almost getting the saturated value. And then we, after getting the saturated value, we check the thermal stability of the photo-induced metastable state when we increase the temperature from 10 Kelvin to 250 Kelvin using 0.2 Kelvin per minute sweeping rate. And you can see the photo-induced metastable state also relax back to the ground state, diamagnetic state, that is roughly around 90 Kelvin. And also there is a small artifact you can see, that is also signature of the photo-induced effect at high temperature. And you can see from the histogram that 780 and 800 nanometer light. They are the most efficient light to convert the diamagnetic state to the paramagnetic state. So what we have done, we use the thin film of the system and we irradiate the system in using the squid magnetometer using 830 nanometer laser light that is available in the lab, and we first cool down the systems to 10 Kelvin. Then we use this 830 nanometer laser light, and you can see here is the we use very small power of the light, 3 milliwatt per centimeter square, and in 1 Tesla magnetic field you can see roughly around 400 nanometer. The system is converting from diamagnetic to the paramagnetic state. And then we have studied the magnetic property of the photo-induced metastable state, and you can see there is a small increase that is coming from the ferromagnetic interaction between the two different chains, and the metamagnetic state that is relaxed back roughly around 80 Kelvin. That is matches very well with the data that is available for the optical reflectivity measurements. So you can see here the paramagnetic high spin state is relaxed back to the diamagnetic ground state as roughly around 80 Kelvin. Then we saw that we studied the AC magnetic measurement of the photo-induced metastable state using external DC magnetic field from 0 ohm to 5000 ohm, but unfortunately we have not observed in this experimental range any slow relaxation of the magnetization on this system. And then what we have performed, we thought, let's see to check the variable temperature IR data from room temperature to high temperature, because below room temperature the system is completely diamagnetic. So what we have observed, at approximately 355 Kelvin, there is another peak is coming. This peak I am concentrated about the cyanide bridge, because cyanide stretching frequency will give you an interesting idea about the spin state as well as the oxidation state of the bridging metal centers. So you can see this band roughly around 2083 centimeter inverse. That is for the diamagnetic iron 2 low spin connected with cyanide bridge by using a Cobalt 2 low spin center, and anything above 2115 centimeter inverse, that is for the iron 3 low spin cyanide Cobalt 2 high spin systems. So you can see when you increase the systems above 355 Kelvin, there is a peak coming around 2153 centimeter inverse, and when you decrease the temperature, then this peak is vanishing. You can see here, and the intensity, or again one can see that the intensity of this 2069 centimeter inverse peak, that is also vanishing when you increase the temperature. So that is also suggesting that there is electron transport is taking place in this center at the high temperature. And you can see here when you do the DSC data, you can see there is a nice peak at a rough center at around 345 Kelvin. That is also suggesting that there is electron transfer or fast order phase transition is going on in the systems. And you can see the system is almost up to 350 Kelvin. And then what we have observed in the Kite versus T plot, when we hit the system above 350 Kelvin, there is a sharp increase in the Kite value. That is also suggesting that the metal to metal electron transfer happening at high temperature. And then when you decrease the temperature, it is following another path, and then it is having very interesting hysteresis. It is showing very interesting hysteresis at below room temperature. And so, and what we have also observed that before 300 Kelvin, below 300 Kelvin, the system was in green in color. But when you increase the temperature of 345, the crystal color changed to almost red, and this is showing a different magnetic property. And then what we have done, we have performed the optical reflectivity, and now you can see here also this partially dissolved system, and we have got the structure also. What we have observed, that here we have the water molecule, the acetyl molecule is no longer there in the crystal structure, and you can see that this molecule is also showing somehow photoactivity, and you can see that at 280 Kelvin the reflectivity curve at 280 Kelvin and 10 Kelvin before and after radiation, there is a huge change in the optical reflectivity curve, particularly this region, and also a particular 800 nanometer region and also 500 nanometer region. And also we have observed that using the white light at 10 Kelvin, we can irradiate the sample and you can get the saturated value of approximately 100 minutes. Then another interesting thing, what we have observed, if you compare it, I'll show you the comparison plot. This is the completely solvable system. So where you can see that the KT, when after the photo-induced magnetic metastable state that is relaxing back to 90 Kelvin, here you can see the photo-induced state is relaxing approximately 150 Kelvin, almost 80 Kelvin shift is there. And not only that, you can see below room temperature, they're all dimagnetic, but here you can see that approximately 200 Kelvin, the system is showing again the metal to metal electron transfer. And what we have observed also in the M versus KT versus T plot, approximately 160 Kelvin, this is completely dimagnetic. But when we quench the system, because as I mentioned to you that this system, after losing the acetonitrile molecule, it is completely paramagnetic, then we can quench the system at low temperature. You can see the quench state is relaxing back to approximately 140 Kelvin. And then what we did, when you cool down the system slowly at low temperature, then you irradiate the systems using 830 nanometer light. That is also why we use 830 nanometer light. That is from the optical reflectivity measurement, and we observe that 830 nanometer light is the highest irradiating light that is showing the maximum conversion between the diamagnetic to paramagnetic. And at low temperature, at 10 Kelvin, we irradiated the system, and you can see the system is converting completely diamagnetic to the paramagnetic state. And then the system is relaxing back. This photo-induced metastable state is relaxing back approximately 120 Kelvin. And again, when you increase the temperature, we can observe there is a electron transfer, metal to metal electron transfer taking place under when you increase the temperature. And you can see only half of the molecule is converting to the paramagnetic state. And then when you increase it again at high temperature, because in the optical using this photometric setup, we cannot go to very high temperature, so we have not measured it above room temperature. But we have performed this measurement using normal DC measurements. So there we have observed that the system is showing two-step electron transfer. And here is the comparison plot, and you can see that the red curve is after light irradiation, and the blue curve is when it quenches the system. And you can see we can successfully quench almost the full state of the systems, and the quenching state is completely different than the photo-induced metastable state. And other interesting things happen when you remove. We thought if you remove the water molecule from the system, what will happen? So we got the crystal structure, and you can see there is no solvent molecule present in the system, and the color of the systems is also changed to completely red in color. And you can see the system is completely paramagnetic in nature. And even at low temperature, we do not observe any metal to metal electron transfer. And you can see this is matches very well with the iron 2. Iron 3 is in the low spin state is equal to half system, and cobalt 2 in high spin state is equal to 3 half systems. And also M/H plot at low temperature is also suggesting that the paramagnetic ground state of this system. And then we have performed the optical reflectivity measurements of the mononuclear systems, and where you can see that there is a small, you can see the blue and the red curve, there is a small light effect in these systems also we have observed. And you can see at 10 Kelvin, but if you see we have observed some metal to metal electron transfer, but also the effect is very weak in case of this iron 4, cobalt 5 mononuclear systems. And the system is also, the metastable state is also relaxing back to approximately 60 Kelvin. And you can see that system is almost showing there is no metal to metal, thermo-induced metal to metal electron transfer observed above near room temperature. And you can see that 800 nanometer light is showing the maximum effect from the histogram plot. And when you measure the magnetic property from room temperature to low temperature, it is showing only the signature of the cobalt 2 high spin. We have not observed any metal to metal electron transfer in this nuclear unit or in the below this nuclear unit. Only we have observed the KT value coming from this cobalt 2 tetrahedral high spin systems. So here is, you can see that the system is composed with iron 2 low spin and cobalt 3 low spin. There is diamagnetic, and you have only cobalt 2 high spin, and this is the signature of cobalt 2 high spin, and this is also matches well. The ground state is mainly with the cobalt 2 high speed present in these systems. And what we have observed, you can see when you measure the measurements under 0 decibel, we have observed there is a small maxima is coming out in the pi second prime. Using the external DC magnetic field, and then you can see there is a in the chi prime and chi second prime versus T, you can see there is a small maxima is coming out. So that is a signature of the single molecule magnetic behavior coming from this Cobalt high speed unit. So in conclusion, what we have observed that ligand field play a very important role in the metal to metal electron transfer process, and also solvent and counter anion play a very important role also in the electron transfer process. You can by changing the solvent molecules in the matrix, you can tune the metal to metal electron transfer process. And we have performed different optical effectivity and magnetic measurements to confirm the metal to metal electron transfer process, and also a photo-induced conversion of the diamagnetic to paramagnetic state is also possible by using light radiation. And also this is the first example of this mononuclear motif, where you can see that there is a metal to metal electron transfer taking place under light radiation, and also this molecule is showing some kind of slow relaxation of magnetization. And then I'd like to thank my institute, Indian Institute of Science, and my funding agency who provided the funding, and also my research group. And thank you very much for your attention.
Thank you very much, Abhi, for your nice and enthusiastic presentation. And we'll take the first question from David.
Yeah, hi, good morning. I have actually two questions. Yeah, can you hear me?
Yeah, David,
okay, perfect. So the first question about the photomagnetic measurements and the estimation of the mass of the sample, because you are discussing the molar susceptibility after irradiation. So I was wondering, how do you estimate the mass of the sample to get these values?
Okay, so usually what we have done actually, so we use this crystals or the fine powder sample, and we put it in the scotch tape. From that you can usually we use 2 to 4 milligram sample that you can easily detect it from the using any kind of sophisticated weighing balance. So usually we are using the same techniques for all our photometric measurement. We are using 2 to 4 milligram sample, not more than that. If you use more than that, then we have observed that if you use more sample, then light cannot penetrate the layer, because if you have a thick layer, you will not observe the maximum highest photomagnetic measurement.
So the second question actually concerns the, I mean, you have shown a bunch of techniques to study these photomagnetic systems, but you didn't show any photocrystallography. I mean, did you try to irradiate compounds using single crystal and measure it?
Yeah, so what we have for the zigzag chain, we try to get the is relaxing back. I can show you here. So you can see that magnetization is relaxing roughly around 80 Kelvin, and in the conventional single crystal lecture using liquid nitrogen, you can go up to 80 Kelvin. So we try to get the structure of the photo-induced state, but we will not get any information, because at the same temperature system is also relaxing back to the diamagnetic state. So you need to go to below. We need to use the helium, but we don't have helium setup here.
Yeah, I know. Yeah, usually the beam lines are synchrotron sources that have this kind of setups. Yeah. Okay, thank you. Very nice work.
Thank you, David. Thank you.
Thanks.
The next question comes from Sergey.
Please, can you show slide number 23? So here, yeah, this one. Here, when you talk about the irradiation of your sample, you mentioned that you measured it at 1 Tesla. Did you observe for any samples the influence of magnetic field to the efficiency of switching?
I cannot.
Can you hear me now? Can you hear me now?
Yeah, I can hear you now.
Yeah? So you mentioned here that you use 1 Tesla to measure the susceptibility. And did you observe for any samples the influence of magnetic field to the efficiency of photo switching?
Yeah, so the main problem from this for this type of systems, because the centering problem is the main problem. If you use a low field, you cannot center the sample very preciously, because they're all dimagnetic sample, and you are using like a tape for almost 10 milligram, and you're using a sample of 2 to 4 milligram. Okay, so if you cannot use, I try to use low field also, because if you use high field, then in that low temperature, you cannot get the interaction properly. You'll miss some information. So that usually we use this 1 Tesla field, because we figure out that if you use this field, you'll get the good data sets. And but again, you have to compensate, like you not get almost all the nice interaction that is possible at low temperature. So we have tried using, I can tell you, using one single crystal that is little big, and to see if you can see the field effect, okay, when you use the high field. So that also we have observed, but that is not significant effect, that much I can tell you. One thing what we have observed, that when you use the you have to have some distance between your sample and the laser tip. When you increase and decrease this laser tip, means the distance between the laser light and the sample, then obviously there will be. Sometimes we observe that when you use the high power of the light, we can see the photo conversion effectively, or even in less time. But again, there is another problem. If you use high power, then you cannot stabilize the temperature, because you are using this 10 Kelvin temperature. So there is a local heating also that will also play a very important role.
So thank you again, Abhi, for your talk. And I think we stop here and we come back at 11 for the next lecture.
Okay. Thank you very much. Thank you. Bye.